add an approval layer where the agent pauses before destructive operations. This approach made sense for stateless chatbots. It breaks down completely for autonomous agents. NVIDIA's team identified the core failure mode clearly. Guardrails living inside the same process they're supposed to be guarding cannot be trusted. A modern long-running agent remembers context across sessions, spawns subagents to act independently, writes its own code to learn new skills mid-task, installs packages, and keeps executing for hours after you've closed your laptop. The attack surface is enormous. Consider the concrete threats. A prompt injection attack can arrive through a malicious web page the agent reads. The injected instruction overrides the original task, and the agent's own behavioral rules now serve the attacker's goals. API keys stored in environment variables become accessible to any code the agent installs. When the agent spawns child agents to parallelize work, those children can inherit parent-level permissions they were never meant to have. And nothing stops a compromised agent from exfiltrating data to an external endpoint, unless the enforcement happens outside the agent's reach. OpenShell's core architectural decision is out-of-process policy enforcement. Instead of relying on behavioral constraints inside the model, it enforces constraints on the environment the agent runs in. The agent cannot override them, even if compromised, because they execute at the infrastructure layer, not the application layer. NVIDIA describes it as the browser tab model applied to agents. Just as a browser tab can't override its own security sandbox, an agent running inside OpenShell can't modify the policies that govern it. Under the hood, all components run as a K3s Kubernetes cluster inside a single Docker container. No separate Kubernetes install required. The OpenShell gateway commands handle provisioning the container and cluster automatically. The architecture has 4 primary components. The gateway is the control plane API that coordinates sandbox lifecycle and acts as the authentication boundary. The sandbox is the isolated runtime with container supervision and policy-enforced egress routing. The policy engine enforces file system, network, and process constraints from the application layer down to the kernel. And the privacy router is a privacy-aware inference routing layer that keeps sensitive context on sandbox. Compute rather than sending it to external APIs. The policy engine enforces across 4 distinct domains. File system policies prevent reads and writes outside allowed paths locked at sandbox creation. Network policies block unauthorized outbound connections, and these are hot reloadable at runtime. Process policies block privilege escalation and dangerous syscalls, also locked at sandbox creation. And inference policies reroute model API calls to controlled backends, also hot reloadable. The distinction between locktat creation and hot reloadable is deliberate. File system and process constraints define the fundamental security boundary of a sandbox. Changing them at runtime would undermine the isolation guarantee. Network and inference policies, by contrast, are operational. You need to be able to open new API endpoints or switch inference backends as work progresses without tearing down a running agent session. What makes the network enforcement particularly powerful is that it operates at the HTTP method and path level, not just IP addresses. An agent can be permitted to call GET on GitHub repositories, but receive an explicit policy denial if it attempts a post to create issues. This is application layer enforcement that understands the semantics of HTTP verbs. When an agent hits a constraint it needs to exceed, it doesn't fail silently. It can reason about the roadblock and propose a policy update. That proposal surfaces to the human operator, who retains final approval. This creates a natural feedback loop where agent capabilities expand incrementally as trust is established, with a full paper trail of every permission grant. The privacy router addresses a problem that's easy to overlook when focused on sandboxing. Where does inference actually happen, and who can see the context being sent? Autonomous agents accumulate significant context over time. User data, internal documents, proprietary code, API responses. When that context reaches a frontier model like Claude or GPT, it leaves your infrastructure. For organizations with compliance requirements, that's a serious problem. OpenShell's privacy router sits between the agent and all inference backends, making routing decisions based on your defined policy, not the agent's judgment. The default posture keeps sensitive context on local compute using open models. Frontier model access requires explicit policy allowance. The router also handles credential management in a thoughtful way. It strips the agent's own API credentials before forwarding to a backend, then injects controlled backend credentials. The agent never needs its own API keys for inference. Compromising the agent does not yield usable credentials for the frontier APIs. OpenShell ships with out-of-the-box support for 5 major coding and autonomous agents: Claude Code, OpenCode, Codex, OpenClaw via Community Image, and Llama via Community Image. Critically, the agent code runs completely unmodified inside OpenShell. The security model requires no changes to the agent harness. OpenShell wraps the environment, not the application. For GPU workloads, OpenShell supports pass-through into sandboxes with a single flag. Combined with the privacy router's default local routing, this enables agent execution that never sends context to external endpoints on your own hardware. OpenShell is part of a broader NVIDIA initiative. NemoClaw bundles OpenShell with NVIDIA's Nematron models and the OpenClaw agent framework into a single deployable package, targeting enterprises that want powerful always-on agents without their data leaving their infrastructure. OpenShell is alpha software with honest limitations. It currently supports single-player mode, one developer, one environment, one gateway. Custom GPU images are required for GPU pass-through. Policy management at scale will need additional tooling, and audit log visualization for compliance workflows is still thin, but the architectural insight is sound and timely. Autonomous agents that run for hours, install packages, spawn subagents, and hold live credentials are in production at forward-leaning organizations right now. OpenShell's core contribution is moving the control point outside the agent, a genuine infrastructure boundary that the agent cannot reason around, prompt inject through, or override by rewriting its own code. Whether NVIDIA's specific implementation becomes the dominant runtime or gets eclipsed by faster-moving open source is an open question. What's not open? The industry needed something like this. Out-of-process policy enforcement is the right architectural frame. And OpenShell is, at minimum, the clearest published thinking on this problem under an open license. The full technical breakdown is available at ThinkSmart, Life/Research, linked below.